Okay, so we have again come back to number theory. Now recall that in the previous video we went through the Euclidean algorithm, using which we can calculate the greatest common divisor of two given integers. We proved the algorithm, that is, we proved the result in the algorithm, and we also illustrated the algorithm with one example, this example. So here we calculated the greatest common divisor of these two integers, and it turns out to be equal to 6. Now a natural question about this whole thing arises: how many steps does it take to calculate the GCD? Say you are given two integers, can we say something about the actual number of steps that one will need in order to calculate the GCD before applying the Euclidean algorithm? And in that direction, here are some things the author is saying. The French mathematician Gabriel Lamy so the time period of his life is given, because anytime in this text we mention someone, we also mention their year of birth and year of death. So he proved that the number of steps that you will require in the Euclidean algorithm is less than or equal to 5 times the number of digits in the smaller integer. Less than or equal to means at most. Steps required in the Euclidean algorithm is at most 5 times the number of digits in the smaller integer. So that just simply means this: say you have two integers a and b, at least one of which is non-zero, so that this GCD exists. In general, you will have something like this. So a is the smaller one, it will have a number of digits in its ordinary decimal expansion. In its ordinary decimal representation, a will have a certain number of digits. If that number is n, then Lamy is saying that the number of steps needed to calculate this GCD by the Euclidean algorithm should be less than or equal to 5n. It should not exceed 5n. It will be at most 5n, but not more than that. So we can take the example of this in example 2.3. The smaller integer namely 3054. It has 4 digits, so the n in this case is 4. So that in the calculation of this GCD by the Euclidean algorithm, we should not have more than 4 times 5, that is 20 steps, which the author is writing like this, so that the total number of divisions cannot be number of divisions cannot be greater than 20. Divisions we are saying because in the Euclidean algorithm we have already seen that each step is an ordinary division. But in actuality, if one goes back to the actual calculation of this that we have in the previous number theory video, one will see that it took exactly 6 steps, so much smaller than this bound, upper bound. So although Lamy's result is only a bound and it does not tell you exactly how many steps you will need in a given specific situation, but it tells you that the number of steps cannot be more than this bound. Now it may not seem like much, but when your numbers become very large, then this bound at least tells you before you start the calculation how many steps are likely to appear. In the worst case possible, you will have exactly this many steps, but it cannot be more than that. That's what Lamy's bound says. Now there is one more thing about this Euclidean algorithm computational aspects. These are computational aspects, right? How many steps are needed and whether, so let us now see the next thing. Another observation of interest. Given any positive integer n, one can find integers a(n) and b(n) such that the Euclidean algorithm will take exactly n steps to calculate the GCD of a(n) and b(n). So that means you can make the Euclidean algorithm run as long as you want. And in fact, exactly, you want, say, for the Euclidean algorithm to run for exactly 100 steps. So if your n is 100, then one can find a pair of integers a100 and b100 such that in the calculation of this GCD of a100 and b100, the Euclidean algorithm will take exactly 100 steps. Okay, so that such pairs of integers can be constructed or can be found. And well, I should not say constructed because I am not sure how the thing is going to be. When we see this thing, we will prove this thing in chapter 13. I haven't gone and seen what we have there actually. So it may not be a construction, it may be an existence proof also. It may be the case that we have, say, some positive integer n given like this in a general way. N is n, and maybe the author is proving that there exists a pair of integers for which this will happen. If it is like that, then it's an existence proof, but it will be better if we could construct such integers. We will see what happens when we prove this fact in chapter 13. So we are still far away from that, so we will see when the time comes. We will prove this fact in chapter 13. Now, when it comes to computational things in mathematics, I mean, you see, it is one thing to find results which look very nice theoretically, and it's an entirely different thing to actually calculate something. And that is why we have this subject known as computer science, where we see how we can calculate things in practice. How about calculability or computability? What sort of difficulties you will have in computation? One such thing is that, you see, it may not seem like much, because what I am trying to say is that, say you want to calculate something in a computer, using a computer or using a handheld calculator, for example. Usually we work with only very small numbers. So it seems like the moment we give some input, the output is almost instant. But the time the calculating machine takes to give you the output is so small that it seems like it's giving it out instantly, but that's not the case. Because the time is so small, we don't see that the time actually it differs depending on your input. If you can generally, you can just simply think of it like this. If your input is large in any sort of computation, then it's likely that the computing device will take some more time to give you the output, because much more work is involved. So what is the relationship between the time the computing machine will take to give you the output based on the size of your input? That is their computational complexity theory. Like you have in computer science those things, but now the thing is that in general, if input size increases, output size also increases. So it's always in our interest to try to, we cannot minimize the input size. The input size is whatever you have, whatever you need to calculate, you just give that as input. Maybe if your number is very large and after the decimal point it has many things, many digits, you can remove some digits, you can do at most that with an input at the expense of losing some accuracy, at the expense of accuracy. But the thing that you can do is that you can make your algorithms or your programs faster by doing something in the program itself. So that is the next thing. Okay, fine. So the Euclidean algorithm is a very systematic and nice way to calculate the GCD of two integers. It is called an algorithm because you can write a computer program based on it. It is so systematic. However, can we reduce the number of steps somehow, by some way? And that is the next thing. It is also one observation, but still it is worth mentioning. One more, it's a remark. And that thing is this: the number of steps in the Euclidean algorithm usually can be reduced by selecting the remainder in a slightly different way than usual. Reduced by selecting or choosing remainders rk plus 1 such that rk divided by 2. Now there are some explanation is needed here. I am coming to that, but before that let us finish this sentence. That is, by working with the least absolute remainders in the divisions. Least absolute that thing that I was discussing just now, that the time a computing machine takes to give you the output depends on the size of the input, you will see an appreciable difference in that time that the machine takes you to give you the output. If the thing you are calculating is not your ordinary addition of two, say, integers or even two real numbers, or the product of a number of real numbers, but something like this, you try to calculate the eigenvalues and eigenvectors of some given complex matrix. So if your matrix becomes very large, then you will see that the computing device takes some time, unless it is some state of the art extremely fast computing device. If you use, for example, Mathematica or Maple, something like that, it will take some time, and the larger your matrix is, the more complicated its entries are, the more time your computer or whatever you are using to calculate these things will take to give you the answer. So there you will see an appreciable difference, and then only you can realize that yes, it takes some time, in spite of the fact that these machines are very fast, but still they take some time, and the longer your input is, the more it will take you, it will take time to give you the output. Least absolute remainders. So that means it's a smart thing to make the algorithm itself faster than what it is, what it ordinarily is. So here is one method. The number of steps in the Euclidean algorithm can be usually reduced by selecting the remainders rk plus 1 such that this. Now, what is the author saying here? You see, when we ordinarily apply the Euclidean algorithm, say we want to calculate the GCD of A and B, where say B is non-zero. What you do when you first apply the Euclidean algorithm, you divide A by B to get a quotient and a remainder R, where your remainder R in general is non-negative and less than the absolute value of the divisor B. Then what you do, say your remainder is actually positive, so you again repeat the process. Now next, dividing B by the remainder, divide the divisor by the remainder, you get another quotient and another remainder, which in general is non-negative and is less than this one. Here, however, you don't need to put the absolute value sign because your R is positive, and the process goes on until you get a zero remainder, and your last non-zero remainder is the GCD. That is the Euclidean algorithm. Now you can see that we eventually arrive at a zero remainder because the remainders are all positive integers, and at every step they are getting reduced in size. So there can be only finitely many of them before we hit a zero value, and that's where the algorithm stops. But can we make it reduce at a much faster rate? We can do that by not applying the ordinary division algorithm at every step, but a slightly modified division algorithm. If you recall, in the first section of the second chapter, we came across one exercise. I think, if I am remembering correctly, it was exercise 7, where we proved something like this. Say A and B are two integers where B is non-zero. Then there exist integers, let me continue here. Then there exist integers Q and R such that A is equal to QB plus R. This part is just like your ordinary division algorithm, but now R is not like your ordinary remainder. R is something else. R satisfies these inequalities. Now if you go to the proof of the Euclidean algorithm, you will see that instead of using our ordinary division algorithm and hence of these ordinary remainders, if one uses this modified division algorithm, then also eventually we reach a zero remainder. And because of the lemma that we proved, remember there was one lemma, and after that lemma only this Euclidean algorithm is coming, and that lemma was just simply this: if we have integers like this, then the GCD of A and B is equal to the GCD of B and R. So if you apply this new modified division algorithm and you carry out a similar set, a series of computations like your ordinary Euclidean algorithm, and you get a zero remainder, in that, over that set of equations also you can apply this lemma, and there also you will see that the last non-zero remainder is the GCD, simply because of this fact, and simply because although the inequalities satisfied by these new remainders are different from your ordinary inequalities that you ordinarily have in the Euclidean algorithm application, these equations remain the same. They have the same structure. So GCD of A and B still is equal to GCD of B and R, and then that reduction continues just like before. But the thing that now you have is that you see the remainders are getting reduced in size at a much faster rate, because previously you only needed R to be just less than the absolute value of B, but now you need that to be less than half of the absolute value of B. So it gets reduced much faster. So you hit the zero remainder much faster, and that is why the number of steps usually gets reduced. But there is one thing, of course, there is a price to pay, and that price to pay is that your last non-zero remainder now is not necessarily positive. So you cannot say that the last non-zero remainder itself is the GCD. However, using this lemma to this new set of equations, you will see that it's very easy to see why that is so, that the last non-zero remainder either is the GCD precisely when it is positive, or it is minus the GCD when it is negative. So it's a minor inconvenience which can easily be, you can make things work by just considering the absolute value of the last non-zero remainder. So that's what the author is saying. At every stage, instead of having the ordinary remainders, we can choose these new remainders from this modified division algorithm which is coming from this. I think I have got the exercise number correct. And these remainders he is saying, calling them least absolute remainders. Okay, but I think these inequalities are not entirely correct. Do you see why? Because the moment we apply the modified division algorithm, our first remainder itself may not be positive. It may itself be negative, because now we are not guaranteed to have positive remainders. And do you see one more thing? These inequalities imply that the absolute value of R is less than, in general, less than or equal to this. You cannot, however, come from here to this one because you need strict inequality here. Anyway, so you get the form of this inequality. So the remainders in this new modified division algorithm behave like this. Okay, each one of them has absolute value less than half of the previous remainder, but here there is a problem because in the previous stage Rk itself may be negative, so you actually need to put an absolute value here as well, where I think the author has made a very small mistake. So you put one absolute value over Rk also. So we hit the zero remainder much faster. So usually the number of steps needed is much less than what we ordinarily have if we apply the ordinary Euclidean algorithm. Now to illustrate this, we calculate the GCD of those two integers that we saw in example 2, 3 that we already calculated in the previous video. Now here with this new type of remainders, and the calculations look like this. Keep in mind that in the previous calculation where we applied our ordinary Euclidean algorithm, it took 6 steps to calculate the GCD. Now let us see how many steps we now need. List absolute remainders in the divisions, of course. Thus, repeating example 2, 3, it is more efficient to write this set of equations. This was the larger integer and the smaller one we know is 3054. So now we again divide this by 3054, but in a different manner. The first one, of course, is just it gives us the original equation itself from the previous calculation. Now, why is this remainder that also appeared previously a remainder like this? That is because 162 turns out to be not just less than 3054, but it also turns out to be less than half of 3054. So this is our new remainder. Now next we divide 3054 by 162, but in the new manner. So we have 19 times 162. I urge you to actually verify these calculations. Okay, so this new remainder minus 24, note that it is minus 24, okay, not just simply 24. The absolute value of minus 24 is 24 and it is less than half of 162. Next, we divide 162 by so the author has written 7 times 24 minus 6 7 times 24 minus 6 will be 162. That is not the problem, but why is he writing 24 though? Because actually we should divide by minus 24. This can be easily modified by just writing the product like this: minus 6 times minus 24. So we are dividing 162 also by minus 24, and at the same time our remainder minus 6, new remainder, has its absolute value 6, which is less than half of the absolute value of minus 24. So you can think of minus 24 here. Okay, so you can see that that's why we need an absolute value here. Absolute value of minus 24 divided by 2 is 12, and the absolute value of minus 6 is 6, so 6 is less than 12. And next we divide minus 24 by 6. So the author seems to have avoided the fact that he is, anyway, let's just not think too much about what Burton was thinking while he wrote these things. Let us just treat these things, these remainders, along with their signs. Okay, the way we are applying in each step, now we are applying the modified division algorithm, where the remainder is, loosely speaking, half the divisor. So we write minus 24 here, and that now gives us minus 4 times minus 6 plus 0. So the last non-zero remainder is minus 6. So GCD is not minus 6. GCD by definition is always positive. So we have to take the absolute value. As evidenced by this set of equations, this scheme is apt to produce the negative S. But note that instead of those original 6 steps, now we have got the job done in only 4 steps. So which is an improvement, and you can we have already discussed why that is so, because we reduce the remainder at every step, not just less than the previous divisor, but less than half of the previous divisor. So things get reduced at a much faster pace. As evidenced by this set of equations, this scheme is apt to produce the negative of the greatest common divisor rather than the GCD itself. One can put up with this minor inconvenience, because in return one is getting less number of steps. Negative of the value of the greatest common divisor of 2 integers rather than the greatest common divisor itself. Okay, now next we come to our next result, actual result, which is a consequence of the Euclidean algorithm. It is this theorem, next theorem. If k is a positive integer, then the greatest common divisor of ka and kb is k times the greatest common divisor of a and b. This condition is needed. Okay, without this condition we will get the sign incorrect. If your k is a non-zero integer but is not positive, then you cannot take k outside just like that, because your GCD of a and b is by definition positive. This thing also is by definition positive, so whatever you are taking outside should itself it should also be positive. And the proof is very easy. All you have to do is you have to write the set of equations that you normally have when you apply the Euclidean algorithm in the calculation of this. You have a set of equations and you have some accompanying inequalities of the remainders satisfying those inequalities. You just multiply everything in that system of equations and all those inequalities by this positive integer k. So precisely this is what the author is saying. If each of the equations appearing in the Euclidean algorithm for a and b is multiplied by k, then we get another system of equations like this. So assuming that b is non-zero, and in the first step we are dividing a by b, I mean in our ordinary Euclidean algorithm, in calculating the GCD of a and b, we have a equal to qb plus r, but it's not just simply q. We had a specific way of assigning suffixes q1 b plus r1, where we had this. Okay, but the author is not using absolute value. Okay, anyway, let us just assume that our a and b are not necessarily both positive, so we use absolute value. What we then do, we divide b by r1 So you get the next quotient Q2 R1 plus the next remainder R2, and we have like this, and it continues. At some stage we get Rn minus 2 equal to Q, what will it be? One more, no? Qn, no, one more in the remainder by which we are dividing, okay? Here we have Qn, and here we have one more, and then this suffix Rn minus 1 plus Rn, new quotient, new remainder, and this Rn is less than the previous remainder, and finally Rn minus 1 is divisible by Rn. Plus 0, so here the process stops, and the GCD of A and B is the last non-zero remainder Rn. Now what we are saying here is that we are going to multiply everything out by k. So that means A is AK and or Ka, okay, we can write Ka. Ka is equal to this times Kb Kr1, and Kr1 is less than k times absolute value of b, but because k itself is positive, so k is equal to absolute value of k, so that means we can place the k inside of absolute value, like that. Kb is equal to Q2 Kr1 plus Kr2, and Kr2 is less than Kr1. Note that we are able to multiply the inequalities also without any problem by k, because k is positive. So we really need positivity here, not just simply for the fact that we want this equation to be correct, but here we need positivity of k in an essential manner. Next, Krn, where Krn is less than k times Rn minus 1, and this of course is 0. But now look at this new set of equations. Is it not just the Euclidean algorithm in the calculation of GCD of Ka and Kb? Because you see, if you divide Ka by Kb, then you are already getting an equation like this, where it seems that Q1 is the quotient and Kr1 is the remainder. But is Kr1 really the remainder? Yes, it is, because Kr1 satisfies the requisite inequalities also. So actually when you divide Ka by Kb, the quotient is in fact Q1 and the remainder is actually Kr1. And the same can be said about the other equations. So that is why the author writes, but this clearly is the Euclidean algorithm, but this clearly is the Euclidean algorithm applied to the integers Ka and Kb. So that means here also the last non-zero remainder would be the GCD of K and KB, and that last non-zero remainder is KRN. So that their greatest common divisor when you hear me talking about things which are from some other parts of mathematics or from other subjects, it is not because I know very well about those things. It is because I don't know about those things, so I am interested to learn. For example, I talked a little about computational complexity theory. I only know that much what I said. I want to learn, so that's why I am enthusiastic. Whatever we have learned, that is fine, that is okay, but then next what? Okay, so that their greatest common divisor is the last non-zero remainder, which is KRN, and the latter number is K times GCD of A and B, because before we multiplied everything out by K, Rn was our last non-zero remainder when we ran the process for A and B. So Rn is the GCD of A and B. So now the GCD of Ka and Kb turns out to be K times GCD of A and B. That's what we wanted to show. So here the proof ends. Now there is a corollary to this theorem which addresses that thing, that if you don't have a positive k but only just a non-zero k, then what happens? For any integer k not equal to 0, the GCD of Ka and Kb is equal to, this time you have to make this thing which you are going to write outside positive. So that's why you need absolute value. Note that we don't really need these integers to be positive, because this also makes sense. For example, this is equal to 2. Just like the fact that GCD of 2 and 12 is 2, GCD of minus 2 and 12 is also 2. So integers here of which you are going to find the greatest common divisor, they themselves may be negative. In fact, both of them may also be negative, it does not matter. But what you are writing outside here, because of positivity of these two things, this must also be positive. Now if k is greater than 0, we need not do anything, because that is the case we handled in the previous theorem. So in the proof of this corollary, it's enough for us to only consider the case where k is negative. So it suffices to consider the case where k is negative. In this case, we have GCD of Ka and Kb. Now, because the greatest common divisor of two integers does not depend on their sign. This is something we discussed before also. So you can just simply consider their negative versions also. They will have the same GCD. And now because your k is negative, minus k is the same as the absolute value of k. And now you can take things outside because absolute value of k is positive. And in this next step, when we take this absolute value of k outside, we are using the theorem, the previous theorem. So that's how we obtain this corollary. So here the proof of the corollary ends. Now there is an alternate proof of our original theorem 2.7, which is also which is even quicker than this one, provided one is comfortable with these things that the author has written somewhat casually. An alternate proof of theorem 2.7 runs very quickly as follows. The greatest common divisor of Ka and Kb is the, now you need to recall the proof of that theorem where we said that if we are given two integers a and b, at least one of which is non-zero, then their GCD exists, and there exist integers x and y such that the GCD can be written as a combination of a and b using an x and y in this manner. Now if you recall the proof of this itself, there we did what? Do you remember? We considered a set like this. Where u and v they run freely over the set of integers. all combinations of a and b with integral coefficients u and v like this. S is the set of all such combinations. We then showed, using the fact that at least one of these two is non-zero, that this set S has at least one positive integer. And then we used the fact that the set of natural numbers, that is the set of positive integers, is well ordered, and concluded that there exists a least such positive integer d in this set S. And then in the proof we showed that this d is in fact the GCD of a and b. So the GCD of a and b in our proof turns out to be the least positive integer in some set, precisely in this set. So that's what we are now going to say, and we are going to use that fact. So the GCD of Ka and Kb is, by that proof, the smallest positive integer, or what is Burton saying, is the smallest positive integer of the form Kax plus Kby, and that in turn is equal to k times the smallest positive integer, which in turn is equal to k times the smallest positive integer of the form ax plus by. That is because you can take k common out. And there is one more thing. The smallest nature of these things that the author is mentioning here, you have to really argue in your mind, or if you want you can write also, that whatever he is saying here is actually the case, that the smallest positive integer of this form is in fact equal to k times the smallest positive integer of this form. That is, if you have, say, a smallest positive integer, if you find a smallest positive integer of this form for some given k, a and b, then you take k common out, then of course you have, by simple elementary algebra, k times ax plus by, and that ax plus by in fact will be the smallest positive integer if you divide this one by k. Okay, so you can argue, the argument is very simple, that we do in fact have these things. That is, more simply saying, whatever the author is saying here in a somewhat casual hand wavy manner is in fact true. So that's what I was saying. If you are comfortable with this type of arguments and you know that they are true, then this proof is very quick. And this, the smallest positive integer of this form, again by the proof of our original GCD theorem, is nothing but the GCD of A and B. And the latter value is equal to k times the GCD of A and B. Now let us end this video by one illustration of this theorem 27. Illustrating theorem 27. You will now see that this theorem in fact is not just simply a theorem of theoretical interest, but it is in fact very useful. Say you want to calculate the GCD of 12 and 30. What you do, you first notice that 3 divides both of these, or for example 2 divides both of these. We will come to that. I mean, you can either first of all see that 3 divides both of these, or you can observe that 2 divides both of these. It does not matter. So let us consider 3 first. 3 times 4, 3 times 10. So using your theorem with 3 in place of k, 4 in place of A and 10 in place of B, you have this. So previously you had 12 and 30, now you have smaller integers, so your job naturally becomes easier, but it gets even easier than that, because 4 is 2 times 2 and 10 is 2 times 5. So we can still take things outside. 3 times 2 times GCD of 2 and 5. Now we know that 2 and 5 are relatively prime. So their GCD is 1. So this is 6. So in fact, without going through any Euclidean algorithm or something like that, you have been able to find the GCD. However, there is one disadvantage to this entire way of approaching to calculate the GCD. It is that if you cannot figure out that there is some common divisor, then you cannot take those things outside. So don't fool yourself by looking at this calculation and thinking, oh, then why do we need Euclidean algorithm? It's because we need Euclidean algorithm, and it's always much more efficient than this type of methods. It is because knowing the factor of an integer or the factors of some integer, and for that matter knowing whether a given integer is prime or not in the first place itself is a very difficult question. Okay, so it may work well in some such cases, but it's not always the case. If you have some very big unknown integers, then you don't really know about them, in the sense that you don't know their factors. So let alone knowing any common factors that they may have. So, but it's always possible to divide one of them by the other and then run through that process of Euclidean algorithm. So the importance of Euclidean algorithm is not lessened by this result, theorem 27. So here I end this video. If you want to make some remarks, say anything about these things or anything else related to mathematics, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And tomorrow we again have Lie algebra exercises. I mean Gregory Lee's algebra exercises. I should not say Lie algebra, that is a mathematical structure. And on Sunday we have our usual real analysis. So that being said, that's it for tonight. So I sign off. So see you tomorrow with list exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.